Helium is the next level of abstraction above hydrogen, and it is our basic-like quantum programming language. It augments hydrogen, expands on the control flow block system in hydrogen by introducing control flow structures similar to BASIC, and is Turing complete. In this video, we will show how to write a program in Helium. Helium supports conditionals with if statements, increment next loops, repeat until loops, and subroutines. You can include subroutines written in C, which we'll cover at the end. An array is a data structure that allows for data storage in your program. Arrays contain data stored in elements and accessed by an index. Initialize an array by assigning a value to an array name, followed by .index. An array's index is a numerical value starting from 0 that identifies an element of the array. Arrays are sparsely indexed, meaning that you can assign elements out of order without error. Helium arrays contain either all classical or all quantum variables. Elements of different types cannot be stored in the same array. Initialize a classical array by assigning a numerical value to an index, and initialize a quantum array by assigning a qubit to an index. An if statement can be conditioned on a quantum or classical variable. In this example of a quantum if statement, we condition a CNOT gate on qubits B and C based on the state of a control qubit A. We initialize qubits in variables A, B, and C in state 0, and then perform a Hadamard operation on the qubit in A. The commands within the if statement are controlled by qubit A. If the qubit in A is in state 1, we enter the if statement and perform a CNOT operation on the qubits in B and C. In this case, the if statement effectively describes a Toffoli gate. In this quantum if example, we put a square brackets around A since A holds a qubit and is therefore a quantum variable. In this example, if is conditioned on the classical variable A, so we don't use the square brackets. If A is 1, then we perform the code inside the conditional, which applies the X operation to the ancilla qubit. Use the syntax increment next to run a block of code for a known number of iterations. Your increment counter starts from 1 up to and including a target value. First, we initialize a qubit at address A. To initialize 3 qubits at indexes 1 to 3 of a 3-element array qubits, we use the increment command. The increment command opens the loop for I with value 1, then 2, up to 3. For each value of I, the loop initializes a qubit at the ith index of the array. Next closes the loop. The next increment loop builds entanglement. For each element in the array, we apply a Hadamard to the kth qubit, then a CNOT using that qubit as the control, and A as the target. Use the syntax repeat until to repeat the execution of a code block until a particular condition is met. Repeat until checks its condition at the end of each iteration and exits when the condition variable is 1. This makes it function identically to a do-while loop in classical programming. First, we initialize a qubit at address A. We use the repeat command to open the loop, until followed by the condition res closes the loop. At each iteration, we apply a Hadamard gate to A followed by a measurement of A, storing the result in the conditional variable res. The loop exits after observing a measurement of 1. You can include helium and hydrogen files anywhere in your code. We will generate the source code written in the file at that point. For example, we can include a constants file containing different fractions of pi. We include constants.qh in our main.qhe file and call the variables directly from main. Subroutines let you package code you want to reuse. You define a subroutine by starting with the command sub, the subroutine name, and the code, closing it off with nsub. The subroutine entangle contains the code from our for loop example. To call a subroutine, use the command goSub followed by the subroutine name. In this case, it is called entangle. You can write subroutines written in C to implement classical computation in an efficient way. Let's implement an 8-bit qubit adder in C using C2Q. The function add takes two 8-bit numbers as inputs, A and B. The function returns an 8-bit output called result. This C2Q file is a configuration file for the automatic compilation of the C function add to a quantum circuit. In the C2Q file, we specify several options. They are the programming language, the name of your C function, the file name of your C function, your input and output variables along with their specified types. The following options determine the optimization of your C subroutine. Mode determines the gate constructions of your subroutine and has three options. Use Oracle when global phase doesn't matter. For example, inside a Grover search. This minimizes T-gates. Use default to minimize the total gate count, which is the right choice for most cases. Default constructs a circuit using standard reversible logic using X, C0, and Toffoli gates. Use T-depth to minimize T-depth, trading extra qubits and C0s for a shallower T circuit. The in-place option is a Boolean data type. If true, it computes linear gates in place. If false, it does not compute linear gates in place. Qubit reuse is an option to reuse ancilla qubits. If set to true, ancilla qubits which are no longer needed in the computation and can be reused will be reused. This saves qubits but generally increases gate count. If false, ancilla qubits will not be reused during the computation. Do uncompute is an option to uncompute ancilla qubits. If true, it reverses the circuit to return ancilla qubits to the ground state. If false, ancilla qubits will not be reversed after computation. In the Helium file, we can then call the include keyword to include the adder.c2q file. We initialize 16 qubits and store them in a special input array starting from index 1. This array stores the input bits for our two numbers A and B. The first 8 bits represents the binary for A, and the next 8 bits represent the binary for B. The least significant bits for our two numbers are stored at input 1 and input 9. We can use X gates to set the bits of each number we're going to add before running our C2Q subroutine. GoSubAdder then calls the C2Q file which executes the subroutine. We obtain the results of our C2Q subroutine in a special output array. You've now learned about programming in Helium, and we hope that you'll enjoy triple alpha and find it useful. To learn more about writing in our programming languages and the instruction set, please refer to our other videos. Happy coding!